that basically models the second moment, the conditional second moment. We have to translate it again to our standard regression model, y, x, and so on. So our y vector is now given by, because we have 5 legs now here in the equation for the variance, so we have to start with epsilon 6 squared. And the second element in our y vector would be the epsilon 7 hat squared. The last element would be epsilon t hat squared. Yeah. So our y vector is now a t minus 5 by 1 vector. So our X matrix, how is this guy defined? So again, we have obviously a vector of 1s in the first column, and in the second, so the first element in the second column is the lag value of epsilon at time t is 6 squared, so which is obviously the epsilon squared hat at time t is 5. Yeah. The corresponding lag to the second element here in our dependent variable, which is epsilon 7 hat squared, is obviously then epsilon 6 hat squared, yeah, and so on. And we end up here with epsilon t minus 5 hat squared. So in the same manner, now we have to lag these guys here, because it's one more lagged, and this happens 5 times. So the next guy would be obviously epsilon hat at time t is 4 squared. Here it would be then at time t is 5 squared. We would end up at epsilon hat squared at time t minus 4. Yeah. And so on. Yeah. So you can just go with it straightforward. So the last guy here, which corresponds to the last regressor in our X matrix, would be then obviously epsilon at time t is 1 hat squared. Yeah. 5, 4, 3, 2, 1. And the second element would be then, of course, the epsilon hat squared at time t is 2. And the last element here would be the epsilon hat squared at time capital T minus 1. So our X matrix has obviously the dimension T minus 5 by 6, right? Because we have 5 regressors and the intercept term. Yeah? So that's now our X matrix that we have to construct. Yeah? And of course, depending on the order P that we chose, if we have a larger P, if P is 10, obviously this matrix here expands. Yeah? And it gets shorter because obviously we lose degrees of freedom. Yeah? This would be then T minus capital T minus 10. And here we would have also a T minus 10 by 1 vector. So everything is straightforward. Our beta vector in this context would be then obviously a vector of W0, W1, W2, and so on until W5. So this would be then a 6 by 1 vector, yeah? Because we have this intercept term, and in addition 5 exposures against past squared regression residuals that are in the mean equation, from the mean equation. So once we have done that, we can simply, we have now defined our matrices, we can again simply employ our standard formula. Beta hat is equal to x transposed x inverted x transposed y. And what we get is then the estimated parameter vector beta consisting of the estimated w's. Yeah? And now what we have to bear in mind is the so-called stability condition. The stability condition means that the sum from I is 1 to capital P of our estimates, W hat I, yeah, should be smaller than 1. Yeah. So if we sum up all of these elements here from W1 to 5, so the exposures W1 to W5 against the past squared lagged residuals, it should be smaller than 1, because what would happen if this is larger than 1? This would be larger than 1, the process would be integrated, right? Because as time passes, the volatility, the conditional volatility in the future is expected to rise and rise and rise. Yeah? It would become larger and larger and larger. We would have an integrated process going on here. So that's why we need to ensure, we need to check if these guys sum up to something that is less than 1. Okay? That's the so-called stability condition. So that's what we are doing, yeah. And again, of course, you can estimate we can estimate the t statistics of our vector, of our parameter vector, yeah. Which of these guys actually are significant, which lags or which lagged residuals, squared residuals, have a significant impact actually on future volatility. Yeah, and of course it's the same thing. We know already how to estimate that. So the variance of our point estimator is defined as 1 over this guy here, hat transpose times itself, yeah, times our matrix X transpose X inverted. Yeah. So what we get is a covariance matrix, obviously, that has a dimension 6 by 6. It must have dimension 6 by 6. And on the main diagonal, yeah, we have the corresponding variances of our point estimators. We know that, yeah. We have 6 elements on the main diagonal. What we have to do is, okay, in order to get the t statistic, obviously, we have to grab each corresponding point estimator from our parameter vector and divide it by the square root of the corresponding element on the main diagonal. Yeah, that's how we get the t statistic in our simple OLS regression framework. Yeah, very simple. It's the same thing that we have done now many times. So the question arises now, okay, so that's basically how you could model the volatility process of an asset, for instance, or of whatever you have here as a dependent variable. And just in general terms, generally speaking, so that's an arch model. And obviously, if you Google a little bit arch model, you will see that a guy called Engel has been awarded the Nobel Prize. He was the guy who developed this methodology, this arch methodology in 1982 paper. I think it was a 1982 paper, and then in 1986 there was a follow-up paper which introduced so-called GARCH models. So what's the difference between a GARCH model and an arch model? Obviously, it's pretty much the same thing, or it's at least very similar. So what a GARCH model is doing, it basically, if you assume that we have a very long order P, if we have a very long dependency structure in the second moment. So if P is, I don't know, 20 or something. So we have a GARCH 1.1 model. So we would say, okay, we summarize everything that happens after the first leg. Yeah, we summarize the effect of all of the legs here as a sigma square t minus 1. Yeah. So this changes here. Yeah. So we model the variance equation differently. Instead of having many legs here, we have, let's say, only in the GARCH 1.1 model, we have only one leg here, and instead of this one leg, now let's take this away. In a GARCH 1.1 model, so we have obviously only W1 times epsilon squared t minus 1 plus something like, let's say, call it beta times sigma square t minus 1. Yeah. So, and this sigma square t minus 1, it basically has the purpose to summarize everything that happens here. So if we have a very long dependency structure in the data, yeah, it summarizes basically all of these lagged sigma epsilon square t minus e. Yeah. So of course, if we have a lot of data, obviously it's not even necessary to have a GARCH model. You can easily operate with an ARCH model if you have infinite observations. They have the same, basically pretty much the same predictive power, or they describe the data pretty much this, in the same way if we have infinite observations. Obviously we don't have infinite observation, and if we have a very long dependency structure here, then this could make sense. But the difference between a GARCH model and an ARCH model is obviously that in ARCH model you can simply estimate via OLS, yeah, using matrix algebra, and a GARCH model you need to estimate via an approach which is called maximum likelihood estimation. So, but that's actually no problem either, because obviously there are already programs that are free available for maximizing the likelihood function. And another advantage with GARCH models is that you can have different assumptions of the distribution of this ET. Yeah? In our OLS framework, obviously, we assume that it's normally distributed. Yeah? And the OLS estimator and the maximum likelihood estimator coincide to be the same if we have the normal distribution. So if these guys are normally distributed, the OLS estimator is the same like the maximum likelihood estimator, which is a very nice property of OLS estimation procedure. Moreover, people may argue that according to the central limit theorem, in association with the law of large numbers, any distribution converges towards the normal. So that's why our OLS procedure is so appealing, and that's why it's so often used in social science. Yeah, because it's very appealing, and it has you can clearly derive the properties of our estimation procedure. So, but why? Once again, obviously we have in financial markets fat-tailed distributions which are not properly captured by a normal distribution. Yeah? So if we have, for instance, we can, for instance, model that the fat-tailedness of the distribution. We can say, okay, we run a GARCH model instead of an ARCH model, and we want to have a t distribution. We want to allow for a t distribution. Let's say our ET follows a t distribution, and we know a t distribution only depends on the degrees of freedom. Yeah, so a normal distribution is defined by its mean and its variance. A t distribution is defined by its degrees of freedom. So if we have, let's say, 3 degrees of freedom, then we have a very heavily fat-tailed distribution. Yeah. Now the question only arises: does it make any sense? Because obviously, if you have 3 degrees of freedom, the variance isn't defined, right? At least if you have 2 degrees of freedom, it's not defined. I'm not sure about 3 degrees of freedom. But the thing is, if the variance isn't defined, then obviously it doesn't make any sense. We talked about it earlier. Yeah? If the variance isn't defined of the error term, nothing makes any sense. You don't have a t-statistic. The t-statistic is not defined. Okay. So that's obviously then a problem. So that you can then ask, okay, in sample, this is Nassim Taleb's criticism, and I agree on that. So in sample, a GARCH model works perfectly fine. Any GARCH model will fit the data. In sample, you always have a variance. You can always estimate an in-sample variance, because any sample that we have in any data sample in finance or in social science anyways is finite. Yeah? So given a finite sample, you will have a finite variance. But it doesn't mean that the underlying distribution has actually finite properties. Yeah? So, and obviously in stock markets or in asset markets, especially in this new crypto currency markets, so the distributions are far away from normal. Yeah? We have huge outliers, and we can say safely that in these markets the variance is very erratic, and it's probably not defined. Yeah. So anyways, so in my opinion anyways, I'm not that let's say strict, or let's say like Nassim Taleb. Of course I share many of his arguments and views, because it obviously makes sense, but for descriptive purposes I think a GARCH model or an ARCH model, it makes sense if you want to describe something. Yeah? It probably is not useful for making predictions, yeah? Because it usually works only in sample. Okay, so but for describing a phenomenon, it might make sense to use this kind of models. Yeah, but it's a different thing when you want to make predictions. So let's take this away